Hi, everyone. So I'm very pleased to introduce Professor Thomas Weth. And maybe you should sit there.
Okay.
And that's okay. So Professor Weth is a professor in mathematics education from University of Erlangen in Nuremberg. And his interests are in mathematical creativity, computer and math education, algebraic curves, history of mathematical schools, etc. And he comes from the fields of studies for mathematics and physics. He also has experience as school teachers, but mostly he is a researcher in mathematics. And he received his PhD on a topic about understanding I'm sorry, how do you say that? Good in English.
Algebraic curves.
In math education. So you talked today about the beauty of mathematics, and the lecture is not for mathematicians only, it's for the lay public. So I'm sure you'll enjoy your presentation, and I very much enjoy your visit in Israel. So he's very fond of Israel and comes here a lot. Okay. So good.
Thanks so much for the invitation. Before I start, I have some personal words. And when I traveled this morning to Haifa, I made the mistake to visit the Ghetto Fighters Memorial. And as you see, my heart, my soul forces me to apologize for what my parents and my grandparents had done to the Jewish people. So sorry. Let's come to business. First of all, Seavit told you already that it's not a high-level mathematical task. I give you not a high-level mathematical lecture, because let me say so, Seavit has to do with applied mathematics. She uses mathematics for useful things. I personally come from the exactly other corner, from the other direction. For me, I always do use less things with mathematics, but that does not mean that it's senseless. There's a difference, you know. So my point of view regarding mathematics is, mathematics for me is a huge game, a huge playground. You can find and create your own problems, make your own puzzles and so on. I see the useless but beauty side of mathematics. Yeah, that's my point of view. Okay, I want to entertain you a little bit during my lecture. And first of all, I have here an envelope. He will play a role at the end of my lecture. Perhaps I fix this envelope here on the platform and you on the whiteboard, and you take care that I do not touch this envelope during the next hour. That will be important. Yeah? Okay. Well, all in all, I will give you two mathematical magical tricks. This is one of them. And perhaps if you are nice to me, I'm completely the other one. Okay. Let's have a look. Well, back to business. The beauty of mathematics, that mathematicians themselves regard mathematics as a beautiful science and see the beauty in mathematics shows in the citation of Geoffrey Hardy, one of the most famous mathematicians in the last century. He says, the mathematicians' patterns, like the painters or the poets, must be beautiful. Forget the next lines. The last line is an often cited expression. There is no permanent place in the world for ugly mathematics. He says, yeah, mathematics is beautiful. his colleague, a philosopher and mathematician, Bertrand Russell, means mathematics possesses not only truth, but supreme beauty, a beauty cold and oyster-like, that of a sculpture, and so on. Mathematics is beautiful. That the view of beautiness is different from person to person, of course, I found by Mark Twain. Mark Twain is well known, I think, had a long journey through Europe, and he wrote down his adventures. And once he visited a very famous opera house in Germany, in Bayreuth, where each year are some festivals about Wagner, composer. And Mark Twain was attacked by the music of Wagner's Lohengrin at Bayreuth. Perhaps you should know, Lohengrin takes round about 6 or 8 hours, the whole opera. It's crazy. Not the mind. He was attacked by Lohengrin at Bayreuth Opera House, that all of his animal spirits had gone before the halftime break. And he only had one single wish: to be left in peace. And he asks if the German auditors really like this noise, as he calls the music of Wagner, by nature, or if they had learned to estimate it by education. He could not find out. Well, the view of beautiness is very different from person to person. Last citation, Arthur Cayley, means beauty can be felt, but not explained. Well, this could be the end of my lecture, but I will try to explain the beauty of mathematics by under the subjects of elegance, surprise, and fascination. That are the 3 main attributes that I want to give you some examples over the whole range of mathematics. Well, I will begin and start with very, very simple notes. I think this series is well known to everyone. And what does a normal person like me do if he has to add all those numbers? Well, we begin on the left. 1 + 2 is 3, + 3 is 6, + 4 is 10, and so on. And after some misattempts, because I discalculate under the way, I perhaps receive a result. And the elegant way is to add it. Oh, the mouse does not work as on. Add it twice. One way down to up, one way up to down. So I have twice the result, and you see that each pair here equals 101. So you got 200, 100 ones, and the real result is the half, 100 ones, and the result is the half of this, 50. This is elegant and nice. It is beautiful, such an idea. Okay, next example. Everyone knows that a big car costs a lot of money and a little car costs little money. A big car has a lot of space and a little car has a little space. A big car has a lot of power, a small car has little power. And the same is in mathematics. A little triangle has a little circumference, and a large triangle has a large circumference. Same to the areas, little area, large area. This is a normal experience in our life. If I buy a lot of, I have to pay a lot of. As more, as more. And it's logical and natural that the same belongs for the angles. Little triangles have little angles, large triangles have large angles, or little sum of angular measures and large sum of angular measures. I often took my students, gave the task to create the triangle with the largest sum of angles. And they try and find 185 degrees and 186 degrees and so on by measuring. Actually, I know that this can't be true. Okay, how is the next question? Can we, the assumption we find the 180 degrees, the assumption can be confirmed independent of the different types of triangles, small ones, large ones, rectangular ones, and. Can the 180 degree assumption be proved for all thinkable triangles, for large ones, small ones, and so on? And the proof, I think you know it, is absolutely intelligent and absolutely elegant. You just need this parallel line and you are done. Because the red angles are the same, the blue angles are the same, and the green angles are the same. With one line, you have infinite, many cases solved with one single line. That's great. That's beautiful. That is ingenious, simple, elegant, beautiful. We come to the next topic, to be surprised by mathematics. And I want to show you something about the number of pi. I wrote here the first 1,000 digits of pi. I don't know why. I made it with a computer program, and my wife said that in the first line is a mistake. I don't know how many digits of pi you know. Yeah, she could just now tell where the mistake is. Doesn't matter if this 20 is, I don't know why she knows that, how many digits of pi she knows, and not my problem. Okay, these are the first 1,000 digits of pi. Well, and in preparation of this task, I looked where the actual record is of the infinite digits of pi. The actual record is 63 multiplied with 10 powered by 12. If you count any second one digit of pi, you need 2, as we say in German, million. I don't know, billion, million years. I have no idea what 2 million means. So I looked in the internet. This is a time where supposed is the appearance of Homo erectus somewhere in Africa. Yeah, and but for my imagination, it's better. This is a time where the first time manhood created stony tools to shape bones or something like that. Yeah, it's a long time ago. A lot of digits, but we know there are infinite ones. Well, in the computer, pi is represented, I hope all digits are correct, in this way. 1 1 dot, that's correct. 1 1 is 3, as far as good, and the rest. So, and infinite many zeros and ones. And that's the same to anything on a computer. Yeah, I have here a picture of my 2 daughters with some bracelets on their nose, whatever. Yeah, and this picture may be round about, let me say, 10,000 digits. It doesn't matter. 10,000 digits of ones and zeros. Okay, what when I tell you now, what has this picture to do with pi? Okay, the fact is that pi is a normal number. What does it mean? What does it mean that a number is normal? That means that any sequence of zeros and ones of the same length appears with the same probability in the digits. I give you an example what that means. Let's take a sequence of 5 digits, perhaps 0 0 0 0 0 or 1 1 1 1 1, 5 digits. Yeah, and now we look at the first 1,000 digits of pi and look where comes 1 1 1 1 1 and where comes 0 1 0 1 0, and we count them. That's not very correct. You see, it's not correct. Not correct. This is not correct, but doesn't matter. It's not a problem. You see what I want to tell you. If you count the red ones and the green ones, the green appears 24 times, the red round about 23 times in the first 1,000. And this happens if you make 10,000 or million or something like that, then the probability of appearance of those are the same. And if that happens to any length, 2-digit, 3, 4, 5, 6, 7, 8 digits with the same probability, then a number is called a normal one. Okay? This, let it be 10,000 on the nose, has the same probability to appear in the digits of pi as the first 10,000 digits. In other words, this sequence will appear anywhere behind in pi, anywhere. But this was a picture of my daughters. You know, the picture of my daughters is anywhere in pi. And if you take a scanner, put on your photograph on it, you have a sequence of zeros and ones, and you can be sure that your picture is anywhere in pi. The art is to find the correct position. Yeah, that's a problem in that. And to see how huge infinity is. Imagine that one had a camera at the moment of your birth, of your personal birth, and he filmed any second of your life until right now. In my case, I'm an old man, yeah. It's such a staple of CDs. He's a young boy here, or there has a small one, yeah. But it's a finite number of zeros and ones he created. And you can be sure that the movie of your life, of your personal life, appears anywhere in pi. That's surprising. The reason of this power, let me call it power, yeah, is of course the disorder of the digits and the infinity. If they wouldn't be disordered, 1, 0, 1, 0, 1, 0, nothing would be happening, it would be boring. Yeah? The power is accidental, the chaotic, the disordered appearance of the digits. That is a power. Much more surprising is that pi can be calculated by high-ordered expression. You see, in those fractions in the denominator 2, 2, 4, 4, 6, 6, 8, 8, 10, 10, and in the denominator 1, 3, 3, 5, 5, 7, 7, 9, 9, and so on, a high level of order, and in contrast to the disorder of the digits, or this series from Leibniz, or that one with continuous fractions, 1, 3, 5, 7, 9, 11, and here 1, 2, 3, 4 squared. High level of order. And you can now take 2 points of view. One is, don't care, in the total chaos, we will find regularity. We can manage chaos. In regard of my desktop, I see the other direction. Even if I try to find total regularity, I produce total chaos. That's the other line, as you can see those phenomena. Okay, next example for surprising. When I ask my students, what do you think if 0.9999, infinite many nines, is greater than, equal to 1, or less than 1? Most of them take the blue, around about 80%. I always argue that for me, 0.9999 is infinite, because the second line shows, in my imagination, I have a paper, write on it 09. put it on the table. I take 1 second later, the next one, put it on the table. 1 second later, the next one, and the next one, and the next one. I never stop. What else is when I never stop? What else is what infinite big should appear? In my eyes, 0.99999 is much greater than 1. Nobody believes me, but it doesn't matter. Okay, most of my students take the blue solution and opinion. Let's ask what mathematics makes of it. If a mathematician does not know what to do, he writes an X. That means I do not know what I'm doing. X equals 0.9999. Then we can manipulate this expression or this equation by multiplying with 10. We got 10x is 9.9999. That's easy. If you now subtract the lower line from the line above, you on the left side find 9x, and on the right side, all 9s disappear by subtracting, except this one. And so we got 9x equals 9.000. That means that x equals 9. And if x equals, what means that x is 1? That's easy. Yeah. And so we got that 1 equals 0.99999. Okay. Some want another proof. I make it short. 1 divided by 9 is, take your calculator, 0.111111. If you add 1 9s on the left and one and then on the right, you find 2 over 9 is 0.2222. 3 over 9 is 0.3, and so on, and so on, and so on, and so on, until to the 8, until to the 9, and now we have 9 over 9 is 0.9999, but you can transform 9 over 9 to 1, and we have the same result. Yeah? It makes it not better and not more truth. One proof is enough, but it's another way. Okay. Let's go to showtime. First, magic trick. You know this person, Uri Geller. In the 80s, when I was a boy or a young man, he was very, very, very famous and present in German television because he's broke spoons and forks and so on over a million of kilometers. I don't know how far his magic reaches. Well, I will make something like Uri Geller, but much better, because Uri Geller could take influence to future things that happened. I will make something that changes the past. That's much more better than Uri Geller, you know. Okay. Around it, to give you an impression what I want to do, I will ask you to imagine a name, perhaps Peter or something like that, or John, doesn't matter. Then I will ask you to manipulate the letters, not the digits.
Characters.
The characters, to manage, to change the characters in a special way. And then you have a new name in your brain. And after this is done, I will send you by my magic force in my brain some vibrations. They are good vibrations, you can rely on. And so I will force all of you to have the same name thought in the past that I want. Okay, so it's complicated. Let's make it with mathematics. That's more easy. Okay. Oh, that doesn't work. Hanan, I want to present this one. Oh, thanks. Okay. The task is, we don't know, take names, that's too long. Take a two-digit number, two-digit. Perhaps I'll come and I'll give you an example. Let's take 55, 55. No, 55 is bad. 56, 56. And now you can take the sum of the digits, 5 plus 6, 11. Okay? And now you subtract the sum of those digits from the original number. Okay? You are done? And this result you will find here on the table with a symbol. If you have 70, you have a square or so and so on. Okay? So let's start the experiment. Take a two-digit number, add the two digits, subtract the sum from your original number, and you have the result. Okay? Everyone has a result. Look for the symbol that is represented. And now I will give you my magic vibrations. Okay, enough. Hanan, it works, it works. Okay. And now you have your symbol in your head. Who has another symbol? Then you have miscalculated. Once again, we do it once again. Take any number.
No, I had it because
You had it.
I had it.
Yeah, if all of you had it,
Yes.
let's repeat it. I have a strong brain. I manipulate it once again. Yeah. Okay, come on. Two-digit number. Subtract, find the symbol. You got it? Ready, done, and any questions? No. Hanan, give me my presentation, please. At this point, I actually received some applause, you know. No. Okay, just kidding. Okay, where is the trick? There's no trick. So this is absolutely simple mathematics. What we did. Look, what we did. We had a two-digit number, AB, and we subtracted well, I don't know what the expression in English is. We subtracted the sum of the digits, yeah, and AB means in decimal system A multiplied with 10 plus with B minus the digits. Okay, that's not very surprising right now. And now we can manipulate it a little bit, and we find 9A as a result. What means anytime you subtract the sum of the digits from a number, you will find a multiple of 9. And now have a look. All multiples of 9, where you landed automatically, have the same symbol. Except the green ones. Except the green ones, because they cannot be reached if you do this. Take any number over 81. Let's take the 96. We have to subtract 15 and we land here. But all multiples of 9 have the same symbol. That's a whole trick. And in the next run, we change all symbols, change the waves, the double waves here, and we can repeat and wonder what happened. Okay. Back to serious business. This is Earth. I put a rope, this yellow rope, on the surface of Earth. That makes round about 42,000 kilometers, roundabout. Okay. Now I cut this rope and put in 1 meter and make it a circle again. You know? And the question is, how far is a new circle from the surface of Earth? How far is it? will it happen that I can put a sheet of paper under the new rope? How far is it away?
You added 1 meter to
1 meter, 1 meter at all. We have 42,000 kilometers plus 1 meter. Okay, it's nothing. Okay, let's ask mathematics. This is a new rope. Absolutely wrong in the dimension, it's clear, yeah, but just for imagination. So, well, let's calculate the problem. We have the radius of Earth, and the length of the yellow original rope is 2 pi multiplied with the radius of Earth, of course. Well, the new one is 1 meter more circumference, 1 meter more. As a radius of Earth plus this h, what I want to know. This one, this red part, I want to calculate, okay? That's a problem. Now I have 2 equations. I can torture them a little bit. That's easy. Come on. We can multiply the right side and find 2 pi r e. And 2 pi r e, this one from, it's the same as this one. The same length, of course. Okay. We got this one. And now you see you can subtract on both sides the L, what means that remains 1 meter is 2 pi multiplied with the distance I'm looking for. And perhaps you can calculate it by brain. That's amazing. It's around about 16 centimeters. 1 meter manipulated of 42,000 kilometers makes 16 centimeters. That's much. It's crazy. Well, and that happens independent of the R. The R in the radius of Earth fell out of the equations. That means if you make the same with the sun, you get 16 centimeters distance. If you make it with a coin, you get 16 centimeters distance. Or with a pinhead, you have 16 centimeters distance. It's a universal constant. It's crazy. Yeah. Well, I did not understand this phenomenon. I did not understand it and tried to make it understandable. To make it understandable, I have the Earth. And because I'm a little bit a mathematician, I try to make life easy. And much more easy than pi or a circle or a bowl, whatever. Then the Earth, sphere. Sorry. It's much more easy is a cube. So I made a cubic Earth. It seemed for me to be better manageable. And I put a rope, this, oh, Hanan, come on. Sorry. Please. Oh, yeah, thank you. It's okay. No, I don't want to play it. What do I do? Okay. No, come on.
No, it's there.
Okay, that's not what
Okay. If you want,
can I take the mouse on? Yeah, okay. I find my way. Thank you. Okay. And what I wanted to tell you is that life is easier for me.
If you want to pause it here, click on the same one on the left. Where you did,
Where did it play?
Excuse me?
if you want to pause it.
I want to hold it.
it's here. Same one. It's here. This one is start and
Okay, let's, okay, can you rewind it back? Okay, no, okay. Good, stop it here. Okay, I put the sphere to a cube. seemed to me much more manageable, and put a white rope around it, around the cubic earth. So I could understand it a little bit better. So this is a white rope, you see it. And now I fill in 1 meter of a rope. This way, I cut the rope on up and down and take the parts from each one. Here 25 centimeters and there 25 centimeters. So I have 50 centimeters of my complete meter wasted. That means that those 2 parts are 12.5 centimeters away from the surface of Earth. Now, well, you see what happens if I go further. It's the same on the right and the left. And now everywhere 12.5 centimeters, independent of the largeness of Earth, of the cube, that doesn't matter. So I understand why those 16 centimeters appeared. And now it's easy to imagine how it works with a sphere. And well, let the Earth disappear. Hanan, I would like to change back. Sorry. Okay, thank you. Wow. Let's come to our last point, fascination. In my philosophical view and useless view of mathematics, I see that I regard mathematics as something like a telescope, what I can use to have a look behind the horizon of my single brain. If I look at night in the sky with my eyes, and everyone sees around about 3,500 stars. Of course, if I use a telescope, I can find much, much more. And similar to mathematics. Yeah, mathematics gives me a telescope to have a look behind the horizon of my simple brain. And so I want to show you 2 examples what I mean. Well, when I began to interest me for infinity, I asked students, first graders, and I will translate what they wrote. One means, the question was, what do you understand by infinity? And this girl, Bernadette, means, for me is infinity a lot of homework to do. She writes, yeah. Her colleague from the same class means the sky is infinite, the sea is infinite. Infinite means without any end. And the last line he writes, the universe is infinite. The first grader. That's okay. There in this list is only missing one what many people say, God is infinite. That is missing by him. Okay, but what I want to point out, in the last, the universe is infinite. This 6-7-year-old boy is in prominent companionship with Albert Einstein. He says there are 2 things that are infinite. The one is the universe, the other is the dullness of man. Concerning the universe, I'm not very sure. Yeah, Albert Einstein. Okay, what I want to show you, 2 things. If you take the natural numbers 1, 2, 3, and so on, and put away the half. all odd numbers, you will receive 2, 4, 5, 2, 4, 6, 8, 10, and so on. And clearly you can pair them. In my students, I tell them, you marry the left and you men and women. And if you marry them, and no woman stays at the end, and no man stays at the end, they must have to be exactly the same amount. So I threw away the half of the left list, and it stays the same size. That is one of the unbelievable phenomenons that infinity has prepares for us. It's crazy, and of course you can delete 9. You can make 1 10, 2 20, 3 30, and so on. You can make it as thin as you can throw away as much as you want, and it stays always the same. It's crazy. It's crazy. Fascinating. That in I write it always this way: the infinity of 1, 2, 3 is the same as the infinity of 2, 4, 6, and so on. Yeah. Well, one phenomenon I want to show you now at last is what infinity has much more to show us with mathematical view. In my eyes, infinity is something gray, far away, without any structure. There is nothing, it's far away. I don't reach it with my brain. And now let's have a look through the mathematical telescope. What we need is a concept of a power set, but I'm sure you know what a power set is. A set A is, in my case, simple example, a square, a triangle, and a circle. Okay, and the power set is a set of all subsets. You know what I want to say. The empty set, all one-elemented sets, the two-elemented sets, and the three-elemented. We do not have 4 elements. We are finished. This is a power set. Oh, not more and not less. And one of the most impressive conclusions in mathematics is this simple sentence. Any set has less elements than the according power set. That's easy, we saw it. Yeah, we had 3 elements and the power set had 8 elements. Yeah, okay. The clue is that this proof I wrote by my own already is very short, shows that this theorem is valid for infinite sets. That's the point. A conclusion is surprising on this way, where I will show where the surprise lies. The proof is short and very elegant. The consequences are fascinating. That's a reason why I show you. Well, this is a conclusion, and because the power set is a set by itself, the same conclusion fits for the power set of a set. There's a second line here. And of course, why stop it if it becomes to get beautiful? Let's make further. We can add as many pieces as we want. And if we now take a useful set instead of the A, let's take the natural numbers. We find that the power set of the natural numbers is bigger than the amount of natural numbers itself. It's bigger, not equal, it's bigger. If we take 2 power sets, it's bigger than this one. 3 bigger than this one. 4, 5, 6, 7. And if we write it in my favorite Expansion, yes, thank you. We see that the infinity of the natural numbers is less than the infinity of the power set. This is less than the infinite of the power set of the power set, and so on. We have infinite many different sizes of infinity. And this is a mathematical firework. This is surprising. This is great. And much more than I can imagine. I see it. Mathematics shows me. It's overwhelming. Well, before I come to my last tricks, I wanted to show you something about the absence, the surprise, and the fascination mathematics can give us on very simple examples. And we come to my last mathematical trick. I need your help. Visualize and here a three-digit number. Okay, thank you. Write under number under number. Anything.
Thomas is asking students to write a three-digit number. He's walking around the class now.
Okay, you. And three-digit. Okay, thank you. Now, I will add those numbers. Oh no, can one of you? Come on, make two. Add those numbers. I ask you.
Check it.
Take this envelope, please.
Okay.
No. Okay, yeah. But we know us too good. We are not dependent from each other.
Okay.
Here, thank you.
No.
No.
All right, this is. Yeah, it's okay. All right. Okay, take it. So first of all, Hanan, please read what the sum of the digits is.
1, 3, 1, 2.
Oh. 1, 3, 1, 2. Okay.
1, 2.
Take it. 1, 3, 1, 2.
1, 2.
Hello.
You will hear the correct answer, please.
1, 3, 1, 2.
1, 3, 2.
Ah,
Oh. Okay, you did not miscalculate. Okay. So, well, thanks for your attention. If you have any questions.
Thank you so much. Anyone here has a question before?
Come on, how did it work? It's the first thing I do know my audience, you know. That's common. Is this what was this? Okay, this is a 1, 3, 2, 1. Yeah. Okay, this is the list of the numbers you wrote. Then I went to my desktop and took this one that I had prepared for my lesson. Of course, I knew what will happen then. And it's not a trick, it's not mathematical, it's just cheating. Okay, just cheating. I will I promised you 3, perhaps, if you want. But I need your assistance. Okay, come on. Take your hands this way. Yeah, everyone takes his hands this way. Make what I do. Okay? No. Now, the thumbs down, inside down. You got it? Right. You cross your arms and shrink the fingers. Okay? You got it? Now, shake the little finger. No. Higher. Okay? And then you shrink, put the thumbs up above. What? Hey, do not break your fingers.
How do we do that?
He changes things.
Huh? Once again, come on. So, you must follow. Yeah. Close. Shrink. You must lift. You are two. And now shrink and zack. What's that? You were not high enough. Okay, I show you the okay?
I know.
The trick is you have to do nothing. This one. Close it. And now I say, come on. You know? I separated it. Okay, that's not mathematics, that's just fun.
You did it twice and we didn't notice.
Excuse me?
You did it twice and we didn't notice.
I could
So you're
have
very
done it
good.
5 times. And no. Okay, if you have any questions, please.
Yes, but we have some questions of the students who are online. We have about 40 students online. So I will choose 2 very good questions that I really liked. What do you think is missing in mass education today in Germany or in Israel?
What is missing?
Yes.
Okay. I'm an old man, you know, and what what a problem is not really. The young people are not sillier than my generation or this generation of my parents was. There's no difference. They are clever as we were, no problem. But what I see is that they are not in that way able to torture themselves, to stay 1 hour, 2 hours on one task. That is a difference to my generation. And we were no better mathematicians or something like that, but we had more discipline perhaps. We did not change any 5 minutes what says WhatsApp, what is YouTube, and we were more concentrated, and that is in my eyes a difference. They are not dollars, and we were that can't be a difference. Different is perhaps education, something like discipline. That's a difference. But the difference between Israel and Germany, I have absolutely no idea, because I do not know what Israel makes at school.
And how do you think that what you did today, like the magic, can be used in formal mathematics in schools, etc.?
Well, in my eyes, I try to be honest to my students, not to tell them how important mathematics is for managing my life. It's really not the case. Okay, that's not true, because I earn my money with mathematics. In my special case, it's not true. But in normal life, I never need a Pythagorean theorem or something like that. Yeah, I do not need it, and I try to tell my students the truth. And I say mathematics has a worth at itself. It's beautiful, something like that. I can sometimes make a joke. I can't any lesson. I do not have a magic trick or something like that. Yeah? But I can show them, perhaps with the example of the triangle. Yeah. Hey, that's surprising. I feel a surprise really still today, even if I did it 100 times. Yeah, it's crazy. Yeah, that always 180 degrees. And I try to give this inspiration to my students and tell them that mathematics has like chess, like playing chess. Some people like it and are fascinated by playing chess. And mathematics is the same. And so I do not want, I do not expect that anyone likes mathematics. It's okay if one says, no, that's not my way of wasting time. No, it's okay, yeah. But those who want it, I try to give some of my fascination I feel when I do mathematics.
I think everyone saw it today. And I will just finish with a big thank you. And a lot of students were very touched about the beginning of your lecture today.
As you saw, I was touched by myself. Yeah. Let me forget this, please.
Okay, but I had to say because a lot commented
It's okay.
all that in the chat and online. So thank you very much and applause again.
Thank you.